Hello everyone. In the last lecture, we have proved some properties of the eigenvalues and eigenfunctions. The last property that we proved in the last video was that corresponding to two distinct eigenvalues, whatever eigenfunctions we get, those eigenfunctions are orthogonal. Okay. Now, let us look at one more property of eigenvalues and eigenfunctions. So I think this must be the fourth property. The set of eigenvalues of the second iterated kernel coincide with the set of squares of the eigenvalues of the given kernel. Okay, so this property says that the set of eigenvalues of the second iterated kernel. Okay, so let us suppose say kx comma t is a given kernel, then the second iterated kernel we use the notation as k2x comma t. Okay, and you can always see that in most of the cases k1x comma t is equal to kx comma t, and the second iterated kernel k2x comma t is some other kernel. Okay, we have some nice formula to calculate k2x comma t, but k2x comma t is different from k1x comma t. Okay, given kx comma t, uh, in some of the cases you may observe that they are the same. Okay, but in general k1, the second iterated kernel is different from the given kernel. Okay, so if we are talking about the eigenvalues of the second iterated kernel, this property tells us that there is some relation between the eigenvalues of the second iterated kernel and the eigenvalues of the given kernel, that is kx comma t. Okay, and that relation is the set of eigenvalues of this second iterated kernel is same as the set of squares of the eigenvalues of the given kernel. So suppose if lambda 1, lambda 2 and lambda n, these are the eigenvalues of the given kernel, then the squares of these will be lambda 1 square, lambda 2 square and lambda n square. So this set and the set of eigenvalues of k2x comma t, those two sets will be the same ones. That is what this property tells us. Okay, so we will have to prove this. So initially what we will do is uh, let lambda be some eigenvalue of kx comma t. Okay, then we will show that the square of this lambda is also is a eigenvalue of k2x comma t. Okay, so that is the forward part. Okay, that, or you can say one part of the proof. Then in the second part of the proof, what we will have to do is suppose some number. Let us take that number to be some mu square, or in the proof I may refer to that number as some lambda square. Okay, suppose if this number is a eigenvalue of k2x comma t, then we will show that either lambda or minus lambda, either one from among these, okay, they are it is the eigenvalue of kx comma t. Okay, so those are the two parts of the proof. So to start with, let lambda be the eigenvalue of kernel k x comma t, and the corresponding eigenfunction be phi of x. Okay. Then by the definition of eigenfunction, what do we have? We have this equation, right? Phi of x is equal to lambda times integral k x comma t phi of t dt. Okay, and you also know that we have defined this particular thing, okay, only this much. This we have defined it as the operator k phi. Okay, so this equation I can write it as, in terms of phi is equal to k phi. Okay, now I will take this on the other side and I will write it as I minus k, sorry, into lambda. It should be lambda minus lambda into k of phi is equal to 0. Okay, so I have written this equation in this form. And what is this form? It is the I means the identity operator. So it is I of phi is nothing but phi. So I of phi of x will be phi of x minus lambda times k of phi. So that will be, it is minus lambda times k phi. When you take it on the other side, it becomes plus lambda k phi. And what is lambda k phi? Lambda k phi is nothing but this RHS. Okay, so I have written this equation in this form. Now here you can say that where I is the identity operator. When we operate both sides of this equation with the operator I plus lambda times k. Okay, what will happen to this equation? This equation will become like this: I plus lambda k into I minus lambda k of phi equal to 0. Because here also I am pre-multiplying by the operator I plus lambda k. Okay, but it is operating on 0, so again we will get this 0. Okay, now how do I expand this? We will have to check what this becomes. This becomes nothing but that I of this thing means what? Nothing but this same thing, because I is the identity operator. So it will be this, that is I of phi minus lambda times k of phi. Okay, plus lambda k of this. Okay, so that will be plus lambda k of this full thing, that is I minus lambda k of phi equal to 0. Okay, now again if we expand this, I of phi minus lambda k phi plus lambda k lambda k I of phi, this is I of phi, right? I of phi is what? Phi. So here we will get lambda k phi. So this will be lambda k phi. Okay, and what is this operator? Minus lambda k phi, again operated by this k. So plus into minus minus, it will become lambda square k, k of phi it will become. This is equal to 0. Okay, so if you observe, this term and this term will get cancelled. Okay, we are left with I of phi. I of phi is what? Nothing but phi, because I is the identity operator, minus lambda square times k of phi equal to 0. So if I want to expand this will become, I'm taking this on the other side. So this will be phi of x, okay, equal to, this is lambda square. What is k of something? K of something, k of phi is given by this expression like this. Okay, then k of this something will be given like how? It will be integral of k of x comma t and this k phi of t. Okay, k phi of t dt. Okay, but what is k of phi? K of phi is nothing but integral k x comma t phi of t dt. Okay, now this is a function of x. I want it in terms of t, so I will write it as integral k t comma some s phi of s ds. That I will put it here. Integral k t comma s phi of s ds, and this integration is with respect to, so it is here. Okay, now we can do that interchange of thing. This will be, I will take this outside and this kx comma t inside, so I will get phi of s integral k x comma t k t comma s dt, and outside it is ds, and you can easily see that this is nothing but k2 x comma s, and outside we have phi of s ds. Okay, and it is lambda square. Okay, so what we have got is, we have got the equation phi of x, which is equal to integral k2 x comma s phi of s ds, and outside it is lambda square. And what is this? This is nothing but phi minus lambda square k2 equal to 0, k2 of phi, which is I minus lambda square k2 of phi equal to 0. Okay, so this equation, it clearly tells us that, this equation here, it tells us that this lambda square is the eigenvalue of k2 x comma t, or the of, or it is the eigenvalue of the kernel k2. Okay, because it is satisfying this homogeneous equation. Okay, so we have shown that if lambda is the eigenvalue of kx comma t, then lambda square is the eigenvalue of k2 x comma t. Okay, this t s you can replace it by t in order to relate it with this, but even if you keep it as it is fine. Okay, now we have to prove the other way. So let us suppose take some number which is looking of this form, lambda square is the eigenvalue of k2 x comma t. Okay, so let mu equal to lambda square be the eigenvalue of k2 x comma t, and phi of s be the corresponding eigen function. So it will satisfy the equation which is of this form, that is phi of s is equal to lambda square integral k2 s comma t phi of t dt, which is same as I minus lambda square k2 phi equal to 0. Okay, so or equivalently this we can write it as, because we have already seen that I plus lambda times k2 I minus lambda times k2 of phi equal to 0. Okay. Now, if lambda is eigenvalue of k, sorry, here it should be k, right? Because we have already seen that how this equation leads to this. Okay. So now I am writing this in the expanded form, which is this. Okay. So if lambda is the eigenvalue of k, then we are done. Why? Because what we want to show that if mu which is equal to lambda square is the eigenvalue of k2 x comma t, then we want to find out some eigenvalue of kx comma t such that square of that number is lambda square. Okay. And if we can show that lambda is the eigenvalue of kx comma t, then lambda, the square of that number is lambda square, which we already have. Okay. So if lambda is the eigenvalue of k, then we are done. But if suppose lambda is not the eigenvalue of k, then you can observe this equation carefully. If lambda is the eigenvalue, then this equation here, it is equal to 0. So this is 0 operated by this operator, you will get answer as 0. Okay. But if suppose lambda is not the eigenvalue of k, then this equation is not true, right? Phi of x equal to lambda times integral kx comma t into phi of t dt. This equation is not true if lambda is not the eigenvalue. Okay. If lambda is not the eigenvalue, then phi of x will not be its eigenfunction, and hence we will not get this equation as true. So it tells us that I minus lambda k of phi will be non-zero. Okay. So basically this operator, this equation is not true. This will not be equal to this. Okay. So if I take this on the other side, it will not be equal to 0. Okay. So basically this is not 0. Lambda k, this will not be equal to 0. Okay. So I can call this full thing as some xi of x. Okay. So I will write this. So if lambda is not the eigenvalue of k, then I minus lambda k of phi let us call it as some xi of x, and this is a non-zero function because this is not equal to 0, so it is not identically 0. Xi of x is some non-zero function. Okay. Then what equation we will get from here? We will get this I plus lambda times k of xi of x to be equal to 0. Now, if suppose we have this equation to be equal to 0, what does that mean? It tells us that this is a, this first of all, xi of x is a non-zero function. So xi of x, which is a non-zero function, is a solution of this equation xi of x to be equal to minus lambda integral. Yes, from this equation, if we expand it, we will get this. Okay. And what does this tell us? It tells us that minus lambda is the eigenvalue of kx comma t, because corresponding to minus lambda, we can get one non-zero function, that is xi of x, which is a solution of this homogeneous equation, integral equation. Okay. And therefore this tells us that minus lambda is the eigenvalue of k, and then also we are done, because if minus lambda is the eigenvalue of k, then the square of minus lambda is nothing but lambda square. Okay. And Therefore, we proved that the set of squares of eigenvalues of k and the set of eigenvalues of k2, these two sets are the same ones. Okay. Now let us look at one more property. The multiplicity of any non-zero eigenvalue is finite for every symmetric kernel for which integral from a to b, again integral from a to b, k x comma t, this square dx dt is finite. So this property says that if this quantity is finite, then for every symmetric kernel, whatever eigenvalues we get, their multiplicity will be finite. So let lambda be the eigenvalue of the symmetric kernel k x comma t, and let phi 1 lambda of x, phi 2 lambda of x, and so on, phi n lambda of x be n linearly independent eigenfunctions corresponding to eigenvalue lambda. Okay, so why I can say this sentence that lambda 1 lambda 2 till phi 1 phi 2 till phi n of x be the n linearly independent eigenfunctions, because you know that when we talk about the eigenfunctions, okay, for the homogeneous equation, so the equation is of this form, right? Phi of x is equal to lambda times integral k x comma t phi of t dt. Okay, and if suppose lambda is eigenvalue, then corresponding to this eigenvalue we get the eigenfunction. But if you remember, when we studied the Fredholm alternative theorem, I have told you all that corresponding to one eigenvalue, we will get r linearly independent eigenfunctions. Okay, in most of the problems that we have solved, this r was always equal to 1. That is, we were getting only one eigenfunction. Okay, because the problems were of that type only. Okay, we were getting only 2 cross 2 matrix and so on, so we were getting only one eigenfunction. But in general, corresponding to one eigenvalue, we will have some finite, we will have some r linearly independent eigenfunctions. Okay, so uh, here we will show that this are whatever we are getting, these will be finitely many in number. They cannot be infinite in number. Okay, so if it is the symmetric kernel, then whatever these eigen functions we are getting, this is what we are going to show is finite. Okay, by multiplicity they mean this, that is these functions whatever we get, these will be only finitely many. Okay, uh, so we already know that these many eigen functions we will get. Okay, so we will be showing that whatever these eigen functions we are getting, those they will be finitely many. The linearly independent eigen functions we will be getting only finitely many. Okay, so for this, first let these be the linearly independent eigen functions corresponding to the non-zero eigenvalue, that is lambda. Okay, then you already know that if we have some linearly independent set, okay, and which is also orthogonal, then by using Gram-Schmidt orthonormalization process, we can convert this set to the other set. Let us call those functions as uk of lambda, uk lambda x. Okay, k is going from 1 2 3 till n. Okay, this corresponding to this set, I can create one more set such that these functions will be orthonormal to each other. Okay, and this can be done by using the Gram-Schmidt orthonormalization process, which you study in the linear algebra. Okay, so basically these are the functions, we have them n in number. So corresponding to this set, I can always generate one more set in which we will have the orthonormal system. Okay, then the corresponding to this set, complex conjugate system. So corresponding, then the corresponding complex conjugate system, this can be formed, that is u k lambda of x bar. Okay, and if suppose this is the orthonormal set, and corresponding to this, if I find out its conjugate or the conjugate functions and form a set of that, then that set will also be the orthonormal set. I think this, by using your simple complex analysis, you can prove that. Okay, so this set will also be, this also forms an orthonormal system. Okay, now that I have this orthonormal set, what I will do is I will write this kernel kx comma t in terms of these orthonormal functions. Okay, so this will be like approximately equal to summation, it is running over I a I u I of lambda of x. Okay, and this bar, where this ai are called as the Fourier coefficients of k x comma t And the formula for this is, so I'm writing kx comma t as summation ai ui lambda of x bar, okay, where ai is the Fourier coefficient of kx comma t, and that ai is calculated by this formula kx comma t ui lambda of x, sorry, lambda of t dt. Okay, now why I can write this kx comma t in this form, that reasoning is given by your functional analysis. Now for this particular part, I want you all to read the page number 135 till 138 from the integral equation textbook, that is Kanwal. Okay, you will have to read these pages in order to understand why I can write this kx comma t as approximately equal to this summation, that is in terms of this orthonormal set. If you remember in your functional analysis, you must have studied something called as best approximation and also Ray's-Fisher theorem. Okay, in that theorem what we do is, or in that part, the best approximation, if suppose we have some orthonormal set given, phi 1, phi 2, phi 3, phi n and so on. Okay, and there is some sequence of uh, constants like alpha 1, alpha n, such that this alpha I series is convergent. Okay, then I can write any function f of x as summation of those constants alpha I and the function phi I. Okay, you must have already studied this. It is called as the best approximation theorem, okay, in your functional analysis paper. So by using that idea, I'm writing this kx comma t as approximately equal to this quantity. Only the difference is here you study it only for the one variable, that is f of x, but here this we have it for the two variables kx comma t. It is depending on two variables, but also for two variables it remains valid. The theory why it remains valid, that you have not studied and it's not there for your, okay, but if you understand this for the one variable, you will, it will be easy for you to relate it here. Okay, so kx comma t, I have written it in this form. Now for this equation, I will use the Basel's inequality. Now what is this Basel's inequality? Basel's inequality says that if suppose we have the functions, suppose say phi 1, phi 2 and phi n, these are the linearly independent orthonormal functions. Okay, once I say orthonormal, I need not say that. So, and suppose xi of x is written in the form summation is ai phi I. Okay, where ai is nothing but integral from a to b xi of x phi I of x dx. Okay, so if ai has this form and xi of x is written approximately equal to this summation. Okay, so this quantity is nothing but equal to xi of x. Then for then the Basel's inequality, this can be proved by using functional analysis. I think you all must have already proved also. Xi of x, norm of xi of x is greater than or equal to summation I going from 1 to infinity, that I square. Okay, so basically whatever is this coefficient, mod of that square and its summation, okay, is less than or equal to, or this quantity, this series is bounded by the norm of xi of x. Okay, so I will use this Basel's inequality for this equation. So how that will become it will be of the form. So this AI, first let us write this equation properly. Where AI is integral from a to b k x comma t u I lambda of t dt. Okay. Now, if you observe this AI, this is what u I lambda are the eigen functions. Okay, because we started with phi 1, phi 2, phi n, phi I of lambda, right, which were the eigen functions corresponding to lambda. Okay, then we constructed the corresponding orthonormal set. Okay, and when we construct the corresponding orthonormal set, if you see, what we do is do we take the linear combinations of these functions only. Okay, and therefore whatever orthonormal set we get which is of these functions u I of lambda, these will also be the eigen functions corresponding to eigenvalue lambda. Okay, so whatever are these functions, they will also satisfy the homogeneous Fredholm integral equation, and therefore what will this quantity be equal to? It will be nothing but ui of lambda, ui of lambda of x equal to this thing into lambda. So this is equal to ui of lambda x into lambda inverse. Take that lambda on the other side. Okay, so ai is nothing but this. Okay, so where ai is equal to this associated with kernel k x comma t for a fixed x. Then by applying Bessel's inequality, we get, from here what we will get, what does the Bessel's inequality say? Norm of this square. Okay, so the norm of this quantity square will be what? Integral k x comma t, this dt. So that will be greater than or equal to whatever are these coefficients. So mod of that, and this ai is what? Nothing but this. So that will be summation running over I and mod of that. So this is so symmetric kernel. So even if I take the mod and then the conjugate, so this will be 1 upon lambda square, because if it's the symmetric kernel then the eigenvalue is the real one. So even if I take the mod of this, it will remain as 1 upon lambda. Okay, and we are taking mod square, so it will be 1 upon lambda square into mod of this ui lambda of x, this square. Okay, so this is equation. Then integrating with respect to, again integrating with respect to x, what we will get? we will get that this is integral from a to b, then here dx. I'm making the change in this equation itself. Okay, so this will be integrating with respect to x, so it will be integral from a to b, then dx. But then if you observe, because of the uniform convergence, we will be able to shift the integral and summation sign. So this will be nothing but the integral of this. In fact, I need not go for the uniform convergence here, because this summation will be the finite one. Okay, because I will be going from 1 to n, because we have only finitely many eigen functions here. Okay, so without using that argument, what we will have to say is this integral of this is nothing but integral of this, okay, into dx. Okay, so that is integral from a to b. Now this will be, what is this equal to? So if you see this term integral from a to b mod of ui lambda of x this square dx, this is nothing but norm of ui of lambda the whole square and ui of lambda. These are the orthonormal functions. Orthonormal functions means what? Norm is equal to 1. So norm square is also equal to 1. So this quantity is nothing but equal to 1. And therefore, what we will get here is this quantity is nothing but 1, and we will be left with only 1 upon lambda square. And therefore, we will get here, this will become n into 1 upon lambda square, because that summation will run n times, right? So whatever is that n is less than or equal to this quantity will be less than or equal to this. Okay, and in the theorem it is already given that this quantity is finite. That means this is less than infinity. That tells us that this n is also finite. Okay, and hence we have proved that there are only finitely many those eigen functions which will be linearly independent.